Imagine discovering a cosmic time capsule from the ancient galaxy, older than our entire solar system. On July 1, 2025, astronomers spotted something extraordinary racing through space at an incredible 137,000 miles per hour. This wasn't just any ordinary visitor, it was 3I Atlas, the third confirmed interstellar object ever detected, carrying secrets from a part of the galaxy we've never seen before. Discovery of 3I Atlas. What if I told you that finding an interstellar visitor requires watching the entire sky every single night? That's exactly what happened when the Atlas Survey Telescope in Rio Hurtado, Chile, made astronomical history. On July 1, 2025, this powerful sky scanner detected a faint moving object with the temporary designation A11PL3Z. Initially appearing as just a magnitude 18 point of light, the object was traveling through the border regions of constellations Serpens Cauda and Sagittarius. What made astronomers immediately suspicious was its peculiar motion, moving far too fast for any ordinary solar system object. The discovery observations were quickly submitted to the International Astronomical Union's Minor Planet Center, but follow-up observations from both professional and amateur astronomers around the world revealed something extraordinary. This wasn't bound by our sun's gravity at all. Within hours of the initial detection, telescopes across multiple continents were tracking this mysterious visitor, confirming that humanity had discovered another piece of the cosmic puzzle from beyond our solar neighborhood. The object's unusual path through space immediately suggested it originated from outside our solar system, making it only the third confirmed interstellar visitor in human history. Atlas Survey System. Ever wondered how we can monitor threats from space across the entire globe? The Asteroid Terrestrial Impact Last Alert System represents one of humanity's most ambitious skywatching projects. This network consists of 4 50-centimeter telescopes strategically positioned around the world in locations including Hawaii, Chile, and South Africa. Each telescope boasts an impressive 7.4-degree field of view, about 15 times the diameter of the full moon, allowing them to scan vast areas of sky in single exposures. The system operates with military precision. Each telescope surveys 1/4 of the observable sky 4 times per night at approximately 15-minute intervals. With 110 megapixel CCD cameras, these robotic sentinels can detect objects as faint as magnitude 19, while automatically tracking moving objects across multiple observations. The Chilean facility that discovered 3I Atlas represents the cutting edge of this technology, capable of processing thousands of astronomical images nightly, while automatically flagging potential threats or unusual visitors. This automated detection system has revolutionized our ability to spot cosmic wanderers before they disappear back into the darkness of interstellar space. The network's sophisticated algorithms can distinguish between asteroids, comets, and potentially dangerous objects within minutes of detection, providing crucial early warning capabilities for planetary defense. Object classification and naming. Have you ever witnessed the moment when a mysterious space object transforms from unknown to historically significant? The journey from A11PL3Z to 3I Atlas tells a fascinating story of modern astronomical detective work. Initially, when the object was first spotted on July 1, 2025, it received the temporary designation A11PL3Z, following standard protocols for newly discovered moving objects. Within just 24 hours, observations on July 2, 2025 by multiple observatories including the Canada-France-Hawaii Telescope and Lowell Discovery Telescope revealed something crucial: a faint coma and 3 arcsecond tail. This discovery immediately elevated the object's status from potential asteroid to confirmed comet, fundamentally changing how scientists would study and classify it. The Minor Planet Center then bestowed upon it the prestigious designation 3Y Atlas, where 3I signifies it as the third confirmed interstellar object ever discovered by humanity. Simultaneously, it received the official cometary designation C/2025N1 according to international naming conventions. By the time this announcement was made, astronomers had already collected 122 observations from 31 different observatories worldwide, demonstrating the unprecedented global coordination required to track these elusive cosmic visitors. The rapid classification process highlighted how modern astronomy has evolved to quickly identify and study these rare interstellar objects before they vanish forever. Orbital characteristics. So what does it actually take for an object to completely escape the gravitational grip of our solar system forever? Well, 3I/Atlas possesses orbital characteristics that are honestly nothing short of extraordinary, placing it among the most extreme objects ever studied. Racing through space with a hyperbolic excess velocity of 58 kilometers per second relative to the Sun, this interstellar visitor moves significantly faster than both previous interstellar objects, 1I/Oumuamua at 26 kilometers per second and 2I/Borisov at 32 kilometers per second. Its trajectory follows an extremely hyperbolic orbit, with an orbital eccentricity of 6.141, which is the highest ever recorded for any confirmed interstellar object in human history. This extreme eccentricity makes the comet's path appear almost perfectly straight rather than curved, at least when you look at it from our solar system. 3I/Atlas will reach its closest approach to the Sun on October 29, 2025, passing at a safe distance of 1.36 astronomical units, so that's roughly 203 million kilometers away. Thankfully, Earth remains completely safe during this encounter, as the comet will never approach closer than 1.8 AU to our planet. After its solar encounter, this ancient visitor will continue its relentless journey back into the vast emptiness of interstellar space, carrying with it the gravitational signature of its dramatic passage through our solar system for, well, billions of years to come. Physical properties. So, how do you measure something that's surrounded by a cloud of gas and dust, millions of kilometers away, out there in the depths of space? Determining 3I/Atlas's physical characteristics actually presents some pretty unique challenges, mostly due to its active cometary nature, and all the interference from its surrounding coma. Early estimates suggest the nucleus diameter ranges somewhere between 0.8 to 11 kilometers, though astronomers tend to favor the lower end of this range based on brightness measurements and activity levels. The Gran Telescopio Canarias made a crucial breakthrough between July 2nd and 5th, 2025, determining that the nucleus rotates with a period of 16.79 hours. The brightness variations are only 0.2 magnitudes, which actually suggests a relatively round shape. Color observations using the Palomar 200-inch telescope on July 3, 2025, revealed some fascinating details about its surface composition, a GR color index of 0.43 magnitudes, RI of 0.16 magnitudes, and a spectral slope of about 1.3% per 100 nanometers. The comet's absolute magnitude measures approximately 12, which corresponds to a nuclear radius of roughly 10 kilometers, assuming typical asteroid-like albedo values. These measurements, though, become increasingly difficult as the comet develops a more extensive coma, making it really challenging to distinguish the solid nucleus from all the surrounding ejected material that creates that classic fuzzy appearance. Advanced imaging techniques and computer modeling are being used to separate the nucleus signal from the contaminating coma light. Comet activity features. So what makes 3I/Atlas behave more like 2I/Borisov than the mysterious and inactive 1I/Oumuamua? Unlike the first interstellar visitor, which showed no cometary features whatsoever during its passage, 3I/Atlas actually displays clear signs of vigorous activity even while it's 4.5 astronomical units from the Sun, much farther out than most solar system comets start showing activity. The comet exhibits a distinct fuzzy appearance in telescope images, which indicates a well-developed coma, a cloud of gas and icy dust particles ejected from the nucleus surface as solar radiation heats up volatile materials. Spectroscopic observations by Gemini South and the NASA Infrared Telescope Facility on July 5 and 14, 2025, confirmed that the coma contains water ice and silicate grains with radii of about 10 micrometers. The dust cross-section within 10,000 kilometers of the comet measures 230 square kilometers, assuming an albedo of 0.10. As solar heating intensifies the sublimation process during its approach, micrometer to millimeter scale particles are ejected at speeds ranging from 0.01 to 1 meter per second, resulting in a dust mass loss rate of 0.1 to 1.0 kilograms per second. This activity level suggests the presence of highly volatile ices that have remained frozen for billions of years, potentially preserving ancient chemical signatures from its original star system. Amateur contributions. So, how did citizen scientists around the world help unlock the secrets of this remarkable interstellar visitor? Well, the discovery and characterization of 3I Atlas marked a historic milestone for amateur astronomy communities worldwide. It really shows how modern technology has, democratized space exploration in ways we couldn't have imagined a few decades ago. Let me tell you about Vamshi Kesareddy, a dedicated citizen astronomer. On July 4, 2025, he achieved something pretty remarkable by successfully capturing 3I Atlas using a unistellar telescope and measuring its brightness at 17.8 magnitude. This observation potentially represents the faintest object ever detected by the unistellar network, which just goes to show the incredible capabilities of modern citizen science equipment and automated imaging systems. And there's more. Amateur astronomer Sam Dean made some crucial contributions too, by meticulously identifying additional Atlas prediscovery observations from June 5th to the 25th, 2025. This extended the observational arc and really improved the orbital calculations. Meanwhile, the Las Cumbres Observatory Network, using 0.36-meter telescopes at Haleakala and the 2.0-meter Falks Telescope North, provided essential photometric data. They showed light curve variations of less than 0.2 magnitudes over a 29-hour time span. All these amateur contributions proved absolutely invaluable, as 3I Atlas traveled through star-crowded fields near the galactic center. In fact, professional surveys might have missed it entirely, because the dense stellar background creates confusion in automated detection systems. So it's clear that the passion and dedication of citizen scientists are, honestly, making a real difference in our understanding of the cosmos. Surface composition. So, what can the colors and reflected light from 3I/Atlas actually tell us about its ancient origins in a distant star system? Spectroscopic analysis, reveals some fascinating details about this interstellar wanderer's composition and the environment where it formed billions of years ago. Observations using the Very Large Telescope on July 4th and 5th, 2025, didn't detect clear signs of hydroxides and cyanides gases in the coma, placing upper limits on outgassing rates of about 8.2 times 10 to the 26th molecules per second, and 5.6 times 10 to the 23rd molecules per second, respectively. However, the comet's red spectral characteristics did show up in multiple independent observations, with a spectral slope measuring 18 plus or minus 4% per 1,000 angstroms, making it significantly redder than most solar system comets we've studied. The water ice and silicate mineral composition, detected through infrared spectroscopy, suggests a pretty typical cometary makeup, but the comet's distance from the sun during those early observations meant that many volatile compounds stayed frozen solid. Scientists predict that carbon dioxide and carbon monoxide ices are likely present within 3I/Atlas, though these substances haven't yet been detected as gas emissions. Future observations by the James Webb Space Telescope will provide more detailed compositional analysis as the comet gets closer to the sun and becomes more active, potentially revealing the pristine chemistry preserved from its formation environment. Interstellar object density. So just how common are these cosmic visitors from beyond our solar system wandering through the galaxy? The discovery of 3I/Atlas actually provides crucial insights into the population density of interstellar objects that have been ejected from their parent star systems and now drift through the vast spaces between stars. Based on 3I/Atlas's characteristics and the circumstances of its detection, astronomers calculate a spatial number density of approximately 1 in 1,000 objects per cubic astronomical unit for objects with radii greater than or equal to that of 3I/Atlas. This means that within a cube of space measuring 1 astronomical unit on each side, we might expect to find about 1 object of 3I/Atlas's size or larger every 1,000 such volumes throughout local interstellar space. The rapid succession of interstellar discoveries, first 1I/Oumuamua in October 2017, then 2I/Borisov in August 2019, and now 3I/Atlas in July 2025, suggests these objects may be far more common than previously thought by theoretical models. Statistical models now indicate that millions of such objects likely pass through the outer solar system undetected each year, basically invisible to our current detection capabilities. The Atlas network's improved sensitivity and comprehensive sky coverage now mean we're finally reaching the detection threshold necessary to regularly spot these ancient wanderers from distant stellar neighborhoods. Origins and age speculation. Could 3I/Atlas actually be older than our entire solar system, carrying materials from the early galaxy? The comet's extreme velocity and unusual trajectory provide some tantalizing clues about its ancient origins in a very different cosmic environment. Moving at 58 kilometers per second relative to the Sun, 3I/Atlas likely originated from the Milky Way's thick disk, which is a region populated by older stellar populations that formed when the galaxy was younger and chemically different. This suggests the comet could be at least 7 billion years old, which is significantly older than our 4.6 billion-year-old solar system, and potentially containing pristine materials from the early galaxy. The thick disk connection indicates 3I/Atlas formed around low metallicity stars that existed when heavy elements were much rarer throughout the cosmos. Its high velocity suggests it was violently ejected from its parent system through dramatic gravitational interactions, possibly involving massive planetary bodies or close stellar encounters that flung it into interstellar space. The comet's water-rich composition and early activity patterns support theories that it formed in the outer regions of an ancient planetary system, where volatile ices could condense and survive for billions of years in the cold depths of space. This cosmic time capsule really offers an unprecedented opportunity to study materials that predate our solar system's formation. As 3I/Atlas continues its epic journey toward the Sun, reaching closest approach on October 29, 2025, it carries with it secrets from the ancient galaxy that we're only beginning to unlock. This remarkable visitor reminds us that space is filled with wandering worlds, each telling a unique story of cosmic evolution. For more mind-blowing space discoveries that challenge everything we thought we knew about our universe, make sure to like, share, and subscribe to Space Facts, where the cosmos reveals its greatest mysteries. What if a message from the stars wasn't a radio wave, but a silent flash of light speaking the oldest language in the universe? On October 13, 2025, an interstellar object, thought to be long gone, sent a signal that defied all known physics. It wasn't random noise. It was a mathematical pattern, the same one that shapes galaxies and life itself, detected by two observatories on opposite sides of the Earth at the exact same moment. Let's explore this together.
The night of pulses.
Did the sky blink, or did something blink back? On the night of October 13, 2025, a stunning event unfolded. Two observatories, one in Chile and one in India, registered a bizarre series of light bursts originating from behind the Sun. The source's trajectory matched that of 3I/Atlas, an interstellar visitor that had vanished from view weeks earlier. This wasn't just a random flicker, the pulses were rhythmic and structured. The event immediately brought to mind the work of Harvard astronomer Avi Loeb, who has argued that we must be open to the possibility of extraterrestrial technology. Loeb even proposed a scale where 0 is a purely natural object and higher values suggest artificial origins. The behavior of 3I/Atlas was so precise it would have scored high on that scale. The flashes were faint but distinct, organized into three groups with mathematically significant intervals. At a magnitude of +22, these pulses were at the very edge of what even powerful observatories can detect, requiring long exposure imaging to even register. For such a weak signal to be so clearly structured with a high signal-to-noise ratio was extraordinary, suggesting its origin was something other than chaotic natural processes.
Fibonacci sequence.
Is there a language any intelligence in the universe would understand? The answer is mathematics, and the pulses from 3I/Atlas used one of its most elegant dialects. The intervals between the bursts were precisely 5, 8, and 13 seconds. This isn't a random set of numbers, it's a core section of the Fibonacci sequence. 0, 1, 1, 2, 3, 5, 8, 13, the famous pattern where each number is the sum of the two preceding it. first introduced to the Western world by the Italian mathematician Leonardo of Pisa in his 1202 book Liber Abaci. This sequence is nature's architectural blueprint. It appears in the spiral arms of the M51 Whirlpool galaxy and governs the principle of phyllotaxis, the arrangement of leaves on a plant stem, which often follows Fibonacci ratios to maximize sun exposure. The 19th century mathematician Edward Lucas, who gave the sequence its modern name, studied its properties extensively. The use of this sequence suggests a message designed to be universally recognizable as non-random and biological or structural in nature. For an interstellar object to emit signals matching this pattern was profoundly strange. It was as if it was broadcasting a page from the universe's own design manual.
Double confirmation.
How do you turn a strange anomaly into hard data? You need independent confirmation, and that's exactly what made the 3I Atlas event impossible to dismiss. The Cerro Tololo Inter-American Observatory in Chile and the Mount Abu Infrared Observatory in India, separated by nearly 12,500 kilometers, both recorded the identical pulse sequence. The recordings occurred within the same 1-minute window, starting at 2:41 UTC. This is critical. They used entirely different instruments, one optical, one infrared, and operated on separate tracking systems. The photometric sensors at Cerro Tololo captured the peaks at 2:41:13, 2:41:18, and 2:41:31 UTC. Mirrored spikes appeared in Mount Abu's infrared data with a synchronization of 0.04 seconds. Frank Drake, creator of the famous Drake equation, always emphasized that signal verification is paramount. Potential false positives like atmospheric scintillation, satellite glints, or cosmic ray hits on the CCD sensors were systematically ruled out. The statistical odds of two observatories experiencing an identical complex instrumental error were calculated to be less than 1 in 10 billion. This double detection transformed the event from a potential glitch into a verified phenomenon.
The golden ratio.
What if the message was not just in the timing, but in the light itself? The Fibonacci sequence is directly linked to another fundamental constant, the golden ratio, an irrational number that's approximately equal to 1.618, also known as phi. Back in the 17th century, the astronomer Johannes Kepler marveled at these divine proportions, believing they revealed the universe's geometric harmony. Now, analysis of the 3I/Atlas pulses showed its light wasn't just blinking. Its peak brightness actually scaled with each pulse. The intensity of the second pulse was roughly 1.6 times that of the first, and the third scaled similarly, matching the progression of phi. The physicist Roger Penrose has shown this ratio appears in fundamental physics and the geometry of space-time. To produce such a signal would require a mechanism capable of precise energy modulation, which is, honestly, far beyond random reflections off an asteroid. The energy distribution of the pulses also matched a logarithmic spiral, a form found everywhere from nautilus shells to the arms of hurricanes. This precise scaling across distance, frequency, and intensity simply could not be a random reflection. It had to be intentionally modulated.
The Fatima anniversary.
Could the timing of the signal be as significant as the signal itself? The pulses were detected on October 13, 2025. That date, interestingly, marked the 108th anniversary of the miracle of the sun at Fatima, Portugal. On October 13, 1917, a crowd estimated between 30,000 and 100,000 people claimed to witness the sun dance, spin, and emit brilliant colors. The physicist August Meessen of the Catholic University of Leuven proposed a scientific hypothesis for the event, suggesting a rare solar mirage amplified by retinal distortion. Regardless of the cause, the event is etched in cultural memory. The Condon Report of 1968, which studied UFO phenomena, noted that such mass sightings often have conventional explanations, but the cultural impact remains powerful. The parallel is, really, undeniable. On the exact same day, over a century apart, two events occurred involving a celestial body performing impossible light maneuvers. This bizarre historical echo transformed a scientific mystery into something deeply symbolic, linking a modern signal to a century-old miracle, and forcing even skeptical minds to acknowledge the depth of the coincidence.
NASA's blackout.
When the most powerful eyes on the sky suddenly go dark, you have to ask why. Just hours before the 3I/Atlas pulses were detected, NASA's Solar Dynamics Observatory, or SDO, went offline for scheduled maintenance. The SDO is a workhorse, capturing an image of the sun every 12 seconds, across 10 different wavelengths, and generating nearly 1.5 terabytes of data daily. For it to go dark during such a critical window is, honestly, highly suspicious. Compounding this, the high-rise camera on the Mars Reconnaissance Orbiter, which can resolve objects down to 30 centimeters on Mars, had been inactive since October 1st. Nicola Fox, the head of NASA's Heliophysics division, oversees these missions. The official explanation cited routine calibration overlaps, but for two premier systems to be down simultaneously felt, to many, too convenient. The SDO's atmospheric imaging assembly in particular would have been the perfect instrument to confirm or debunk the pulses directly. Its absence created an unfillable data gap, fueling speculation that this was not maintenance, but a deliberate blackout.
Harmonic resonance.
What if the signal wasn't just a message, but, an activation key? The numbers 5, 8, and 13 might be more than just a sequence. They could correspond to frequencies. The concept of orbital resonance is actually a well-established principle in astrophysics. A prime example is the 1:2:4 resonance of Jupiter's moons Ganymede, Europa, and Io, which was studied by Pierre-Simon Laplace way back in the 18th century. Another example is the Kirkwood gaps in the asteroid belt, those empty regions caused by Jupiter's resonant gravitational pull. Modern celestial mechanics expert Renu Malhotra has even used these principles to predict the structure of the Kuiper belt. So, one interpretation of the 3I/Atlas signal is that it wasn't aimed at our eyes, but at the solar system itself. The pulses, with their precise timing, could have been designed to resonate with key gravitational zones, the 5th harmonic with Earth's orbit, the 8th with the asteroid belt, and the 13th with Jupiter's influence. This would be a form of communication that uses the very architecture of spacetime as its medium, transferring information through gravitational vibrations.
The Dante connection.
Could a 700-year-old poem hold a clue to an interstellar message? In the 14th century, the Italian poet Dante Alighieri wrote Paradiso. In it, he describes heaven as 9 concentric celestial spheres, with their structure governed by precise numerical and geometric principles. The year of Dante's death, 1321, is exactly 704 years before the 2025 event. Physicist and Dante scholar Mark A. Peterson published a famous paper in 1979, arguing that Dante's cosmos wasn't just concentric circles, but a hypersphere, the three-dimensional surface of a four-dimensional ball. The rhythm of ascent in Paradiso mirrors patterns of growth similar to the Fibonacci sequence. Now, this isn't to say Dante predicted the signal, but that the mathematical patterns of order and growth are so universal they appear in both our deepest artistic intuitions and in signals from the cosmos. The idea that an interstellar signal in 2025 would use the same sequence is, honestly, staggering. It raises the haunting possibility that this mathematical pattern is a universal signature of intelligent design, an archetype recognized across cultures, centuries, and perhaps even worlds.
Observatories respond.
After a week of intense public speculation, what did the scientists who saw it first have to say? The official statements from both the Cerro Tololo and Mount Abu observatories were masterpieces of scientific caution. They confirmed the data, captured starting at 2:41 UTC, was real. The timestamps were synchronized and the pulses were consistent across optical and near-infrared bands. But they refused to speculate on the origin. The event was labeled a non-repeating transient photometric anomaly. To a SETI researcher like Jill Tarter, this approach is standard procedure. However, their findings were published in low-profile technical bulletins, not major peer-reviewed journals like Nature or the Astrophysical Journal. This was a strategic choice. It places the data on the record for specialists without inviting a media frenzy. Contrast this with the 2016 announcement of the first detection of gravitational waves, which was a major, coordinated press event. The quiet, almost buried release of the 3I/Atlas data made it clear that the institutions involved did not want to deal with the public implications of their discovery.
The missing data.
Sometimes, the most important clue is the evidence that isn't there. As researchers and the public scrambled for answers, all eyes turned to NASA, whose silence was deafening. The data from the Solar Dynamics Observatory for the entire period of the 3I Atlas event was missing from the public archives. This was a gap where 1.5 terabytes of crucial solar data should have been. There was no error note, just a void. Edward Tufte, a pioneer in data integrity, teaches that such omissions are often more revealing than the data itself. This silence wasn't limited to NASA. The European Space Agency's solar orbiter issued no comment, despite being in a perfect position to observe. The Japan Aerospace Exploration Agency JAXA also remained quiet. NASA has strict protocols for documenting data gaps from missions like the SDO. The complete absence of such documentation was a major breach of their own standards of transparency. This global information blackout became the smoking gun, transforming the narrative from a scientific puzzle into a potential cover-up. So, what are we left with? An interstellar object emits a structured light signal based on a universal mathematical constant. The event occurs on the anniversary of a famous celestial miracle. It's independently confirmed by 2 observatories, only for the world's leading space agencies to go conveniently blind at that exact moment. Was it an impossibly complex series of coincidences, a natural phenomenon beyond our current understanding, or was it exactly what it looked like? A message? A single, simple greeting written in the language of light and mathematics. We may never know for sure, but the silence from those who might have answers is the most unsettling part of all. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the universe's greatest mysteries. Thanks for watching Space Facts. What if a whisper from another galaxy could rattle Earth's planetary defenses? On October 1st, 2025, something 2.5 million light-years away seemingly touched our planet's invisible armor, triggering a scramble inside NASA. This wasn't a solar storm we could predict, it was something entirely new, linking the distant Andromeda galaxy to the radiation belts that shield us all. We're going to break down the signal, the response, and what it means when the cosmos reaches out in unexpected ways. Let's explore this together.
The October 1st discovery.
It began as a day like any other inside NASA's Space Weather Prediction Center. A standard G2 geomagnetic storm watch was issued, implying a KP index of 6 on a scale of 9, but the source was a predictable solar magnetic cloud. But then, the routine broke. At Goddard Space Flight Center, mission controllers noticed odd chatter. Automated queries to the legacy data from the Van Allen probes, officially the Radiation Belt Storm Probes or RBSP mission, began spiking. Someone, or something, was digging through recent radiation belt telemetry, and fast. The access patterns weren't for routine analysis. They matched emergency protocols designed for rapid threat assessment. Whispers started surfacing online. Signals from the Andromeda galaxy, our planet's protective radiation belts, had blinked, and though NASA remained silent publicly, the digital evidence told a story of a new and unexpected cosmic connection. Experts like Dr. Antti Pulkkinen, a renowned heliophysicist at Goddard, would have been among the first to be alerted to such a deviation from established models. The first sign that our understanding of space weather was about to change had arrived not with a bang, but with a series of urgent automated database queries.
The anomalous signal.
Here's what started the entire chain of events. At 3:47 UTC, the Deep Space Network nodes in Goldstone, California and Canberra, Australia, logged a strange radio transient. It lasted only 8 seconds and came directly from the Andromeda sector, a tiny patch of sky less than a degree across. Instantly, it stood out. The signature didn't match any known pulsars or the behavior of cataloged quasars. For a normal solar radio burst, the pattern was all wrong. The signal's intensity, while faint at a flux density of only a few Janskys, was coherent enough to be unmistakable. But the most compelling clue was its frequency. The burst peaked at 408 megahertz. That's a softer, lower frequency than most fast radio bursts, or FRBs, which typically hit between 600 and 1400 megahertz. This detail is critical because lower frequencies like this are known to be in the range that can efficiently interact with and stir up electron motion within Earth's magnetosphere, a process governed by plasma physics. This wasn't just random noise from deep space, it was a signal with a frequency that, theoretically, was perfectly tuned to get a reaction from our planet's protective shields. It was a whisper, but it was a whisper at exactly the right pitch to be heard.
The belt response.
16 minutes after that anomalous signal from Andromeda was detected, something happened much closer to home. NOAA's GOES satellites, sitting in geostationary orbit 35,786 kilometers above Earth, registered a sharp 40% jump in electron count. Specifically, their magnetospheric electron detector or MAGED instrument saw a surge in relativistic electrons with energies greater than 2 mega-electron volts. This wasn't a slow swell you'd expect from solar wind. It was a violent spike in under 3 minutes, 800 times faster than the baseline activity on a quiet night. Ground magnetometers in Tromsø, Norway, and data from the Canadian Charisma network confirmed the fluctuation. The timing was too perfect to be a coincidence. An 8-second radio burst from a galaxy 2.5 million light-years away, followed 16 minutes later by a significant, measurable disturbance in the radiation shield protecting our planet. The data was undeniable. Something had reached across an unimaginable distance and physically nudged the Earth's magnetosphere. The invisible armor of our world had been touched, and now the race was on to understand how. It was a direct challenge to every existing space weather model.
NASA's response protocol.
When Earth's radiation belts move that fast and the sun isn't the obvious culprit, NASA doesn't guess, it executes a playbook. The first call goes to the Space Weather Coordination Center. Step 2 is to pull real-time solar wind data from the DSCOVR satellite, which sits 1 million miles from Earth at the L1 Lagrange point. Its Faraday Cup instrument showed solar wind speeds were a pretty placid 385 kilometers per second, with the interplanetary magnetic field's BI-Z component hovering near zero. No southward tilt that would open a door for solar energy. Step 3 involves comparing magnetometer readings from a global network, from Alaska to Antarctica. On October 1st, none of these standard checks provided an answer. The DST index, a measure of geomagnetic storm strength, was a negligible -8 nanoteslas. With no earthly or solar explanation, the situation was escalated to level 2. This means waking up principal investigators, running predictive models on supercomputers, and immediately checking the position of astronauts on the International Space Station and high-value satellites. The scramble isn't chaos, it's a methodical checklist running against a terrifying new variable, leaving forecasters with data they just couldn't explain.
The physics mystery.
The data left researchers with a series of profound questions. First, the timing offset. The belt's twitch lagged the radio burst by exactly 16 minutes. Since electromagnetic waves travel at light speed, a direct cause and effect should have been instantaneous. This delay suggests a secondary mechanism. Maybe the burst triggered a cascade effect in the plasma waves already surrounding Earth. Second, the frequency mismatch. The Andromeda burst's peak at 408 MHz is unusually low, but it happens to fall squarely in a frequency band known to efficiently transfer energy to trapped particles via Whistler mode chorus waves. Finally, the signature of the disturbance itself. Data hinted at a sharp change in pitch angle distribution, basically how steeply electrons spiral along Earth's magnetic field lines. This suggests they were scattered by a wave pulse, knocking some from stable orbits into the loss cone where they precipitate into the atmosphere. Experts in this field, like Dr. Richard Thorne of UCLA, have built entire careers modeling these wave-particle interactions. These 3 clues, the delay, the resonant frequency, and the scatter signature, pointed away from coincidence and toward a new, unmapped physical mechanism.
Historical surprises.
To understand the shock of this event, you have to know that the Van Allen belts have a history of shattering our assumptions. In September 2012, NASA's Van Allen probes discovered something thought to be impossible. A third, temporary radiation belt materialized between the 2 known belts, located at an L shell of about 3.5. It lasted for 4 weeks before a solar shockwave erased it. The lead investigator, Daniel Baker from the University of Colorado's Laboratory for Atmospheric and Space Physics, stated plainly that our models were wrong. Then in 2014, the same probes found what scientists now call the impenetrable barrier. At an L shell of 2.8 or about 11,000 kilometers altitude, the most energetic ultra-relativistic electrons with energies above 5 MeV simply stop, unable to move closer to Earth. And as recently as May 2024, the SERB-C CubeSat mission confirmed the formation of 2 temporary extra rings, which persisted for months. For over 60 years we've studied these belts, yet they repeatedly prove we don't have the complete picture. They can reconfigure in ways we can't predict. responding to forces we are still struggling to identify.
The resonance mechanism.
The leading theory to explain this event doesn't involve a powerful blast from Andromeda, but something far more subtle: resonance. Think of it like, pushing a child on a swing. You don't need immense strength, you just need to push at the right moment, matching the swing's natural frequency. The Van Allen belts are a resonant system. The trapped particles and magnetic fields have natural frequencies, governed by a process called cyclotron resonance. Researchers like Dr. Wen Li at Boston University have created models showing exactly how specific wave frequencies can pump energy into the electron population. The Andromeda signal, despite traveling 2.5 million light-years, didn't need to be overwhelmingly powerful. It just needed to hit the right note. The burst's 408 MHz frequency may have perfectly matched a natural resonance frequency in the outer belt's plasma. This would allow electrons to efficiently absorb the energy, causing them to change orbits and scatter. It's not science fiction, it's a proven concept. The only question is whether a signal from another galaxy could really be the trigger.
Real-world consequences.
A twitch in the Van Allen belts isn't just an academic curiosity, it has immediate real-world consequences. GPS satellites orbit at 20,200 kilometers, right in the heart of the outer belt. A sudden 40% spike in electron density can degrade the standard positioning service from 3-meter accuracy to over 10 meters, affecting everything from air traffic control to financial systems. Communication satellites can experience temporary outages, causing dropped calls and buffering streams. For astronauts, especially on future Artemis missions, an unexpected radiation spike is a serious health risk, potentially adding several millisieverts of dosage with little warning. In a worst-case scenario, intense radiation can cause permanent satellite damage, as was demonstrated by the early failure of Telstar 1 in 1962 after being exposed to a man-made radiation belt. The systems our modern world is built on are fragile, and they all run under the influence of these unpredictable belts. This event serves as a stark reminder of that vulnerability.
Testing the hypothesis.
So how do scientists move this from a fascinating anomaly to proven fact? It comes down to a rigorous, repeatable process. Step 1 is timestamp alignment. You overlay the logs from radio telescopes like the Kime-Far-B detector in Canada with satellite data from missions like JAXA's Arase probe with microsecond precision. If that 16-minute lag repeats, it points to a real connection. Step 2 is a spectral match. You analyze the frequency of future bursts. If they consistently fall within the resonant bands, the case for a physical mechanism gets stronger. Step 3 is multi-latitude confirmation. You need magnetometers across the globe to register the same event, confirming a planet-wide response. But the most critical test is repetition. 1 event is an anecdote. 2 is a pattern. 3 establishes a phenomenon, worthy of publication in a journal like Nature. If another Andromeda burst occurs and the belts don't respond, the hypothesis is weakened. Both positive and null results are crucial. It's the slow, methodical work that separates real discoveries from sensational claims.
Background science explained.
Let's quickly break down the core science. The Van Allen belts, discovered in 1958 by James Van Allen, are 2 primary donut-shaped zones of charged particles. The inner belt, between 1,000 and 6,000 kilometers altitude, is mostly stable. High energy, protons, in the 10 to 50 MeV range. The outer belt, from 13,000 to 60,000 kilometers, is a dynamic zone of electrons. The primary driver of change is the sun. Solar flares and coronal mass ejections blast particles toward Earth, causing the belts to swell. Inside the magnetosphere, a constant dance of wave-particle interactions is happening. Waves with names like chorus and hiss are always accelerating and scattering these trapped electrons. Deep space signals are also arriving constantly. Fast radio bursts are millisecond flashes from distant galaxies. Pulsars are spinning neutron stars that emit regular beams with millisecond timing precision. The October 1st event suggests a new type of interaction, where a specific radio signal from deep space might be coupling with the natural wave physics already happening in our own backyard, a concept previously confined to theory. So, we stand at a fascinating crossroads. An 8-second radio burst from the Andromeda sector, followed 16 minutes later by a 40% spike in Earth's outer radiation belt. The data is documented, the timing is recorded, and the standard explanations, solar flares, magnetic substorms, don't fit. We're left with a working mystery. Was this a 1 in a billion cosmic coincidence, or have we discovered a new way the universe can interact with our world? The answer will come not from speculation, but from the slow, rigorous process of science. Instruments are watching, data is being gathered. The next signal could be the one that confirms it all. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the science that's reshaping our understanding of the cosmos. What do you think is behind the 16-minute delay? Thank you for watching Space Facts.